Every atom in your body, every photon of light illuminating this screen, every breath of air you take, and every star shining in the night sky represents energy that somehow came into existence 13.8 billion years ago during the Big Bang. Yet one of the most fundamental laws of physics, the conservation of energy, states that energy can neither be created nor destroyed, only transformed from one form to another. This creates what may be the most profound paradox in all of science. If energy cannot be created, where did all the energy in our universe come from? The numbers involved are staggering beyond comprehension. The observable universe contains roughly 1,080 atoms, each representing matter energy equivalent to Einstein's famous E equals mc. Add to this the energy contained in electromagnetic radiation, dark matter, dark energy, and the gravitational fields that bind everything together, and you get a total cosmic energy budget that defies imagination. Every joule of this energy apparently appeared from nothing during the first moments of cosmic expansion, seemingly violating the most basic principle that governs all physical processes. This isn't just an academic puzzle for cosmologists to ponder. This paradox strikes at the heart of how we understand causality, existence, and the fundamental nature of reality itself. If the universe began with the spontaneous creation of enormous amounts of energy, then either our understanding of energy conservation is incomplete, or the Big Bang operated according to principles that transcend the physical laws we observe today. Dr. Alan Guth from MIT, who developed a theory of cosmic inflation, describes the magnitude of this problem. The Big Bang appears to have created something from nothing, which seems to violate every principle of physics we know. Understanding how this is possible, or whether it's even the right question to ask, may be the key to understanding the deepest nature of reality itself. But modern physics has begun to reveal startling solutions to this apparent paradox. Quantum mechanics suggests that empty space is actually seething with energy fluctuations that can spontaneously create matter and antimatter pairs. Inflation theory proposes that the universe underwent a period of exponential expansion that could amplify tiny quantum fluctuations into cosmic structures. And perhaps most surprisingly, calculations of the universe's total energy, including the negative energy stored in gravitational fields, suggest that the cosmic energy budget might actually equal exactly zero. The zero-energy universe hypothesis represents one of the most elegant and mind-bending solutions ever proposed to a scientific paradox. According to this idea, the Big Bang didn't actually create any energy at all. Instead, it separated the universe's zero-energy initial state into positive energy, matter, radiation, kinetic energy, and negative energy, gravitational potential energy. The total remains zero, perfectly conserving energy while creating the appearance of a universe filled with matter and energy. This solution emerges from Einstein's general relativity, which reveals that gravity is not a force in the traditional sense, but a curvature of spacetime itself. In curved spacetime, energy conservation becomes more subtle, with gravitational potential energy acting as a cosmic bookkeeping system that can balance enormous amounts of positive energy with equally enormous amounts of negative gravitational binding energy. But even this elegant solution raises deeper questions. If the universe's total energy is zero, what caused the initial separation into positive and negative components? Why did the Big Bang occur at a specific moment rather than earlier or later? And perhaps most fundamentally, how can we apply concepts like energy conservation to the origin of spacetime itself, when energy conservation depends on the existence of time? Quantum tunneling offers another perspective on cosmic origins, suggesting that the entire universe might have spontaneously tunneled into existence from a quantum vacuum state. Just as subatomic particles can tunnel through energy barriers that classical physics says they cannot cross, the entire cosmos might have tunneled from nothingness into existence without violating any fundamental conservation laws. The multiverse hypothesis pushes these ideas even further, suggesting that our universe might be just one bubble in an infinite foam of universes, each with its own Big Bang and its own allocation of energy from some larger cosmic reservoir. In this framework, energy conservation operates on scales far beyond our observable universe, with individual Big Bangs representing local fluctuations in an eternal, ever-expanding multiverse. Tonight, we're diving into one of the deepest mysteries in all of science, exploring how the apparent violation of energy conservation during the Big Bang has led to revolutionary insights about quantum mechanics, spacetime, and the fundamental nature of existence. You'll discover exactly how physicists calculate the universe's total energy budget, learn about the surprising role that nothing plays in quantum mechanics, and explore cutting-edge theories about how something can indeed come from nothing without violating the laws of physics. We'll investigate the mathematical frameworks that govern energy in expanding universes, examine how inflation theory solves multiple cosmic puzzles simultaneously, and uncover the profound implications of Noether's theorem for understanding what energy conservation really means in a universe where spacetime itself can be created and destroyed. You'll learn about the quantum vacuum and its surprising energy content, discover how gravitational energy can be negative, and how this creates possibilities for cosmic free lunches, and explore the philosophical implications of living in a universe that might have emerged from literally nothing through processes governed by quantum mechanical principles. We'll explore how the Big Bang challenges our understanding of causality and time, investigate whether the concept of before the Big Bang even makes sense, and examine how cutting-edge theories in quantum gravity are attempting to describe the origin of spacetime itself. This isn't just a story about cosmic origins and abstract physics principles. This is about understanding how existence itself is possible, why there is something rather than nothing, and what the apparent violation of energy conservation during the Big Bang reveals about the deepest principles governing reality. The question of where Big Bang energy came from connects to fundamental issues in philosophy, including questions about the nature of causality, the meaning of existence, and whether the universe requires an external cause or can be self-creating through natural physical processes. As we explore this cosmic mystery, you will discover how the apparent paradox of Big Bang energy creation has led to some of the most beautiful and profound insights in theoretical physics, revealing a universe that operates according to principles far stranger and more elegant than our everyday experience suggests. If you're fascinated by the deepest questions about cosmic origins and how they challenge our understanding of physical law, subscribe and hit the thumbs up button. And here's a mind-bending question to consider. If the universe's total energy is exactly zero, does that mean existence itself is just an elaborate illusion created by the separation of nothing into positive and negative components? Comment below with your thoughts. I'll pin the most thought-provoking philosophical reasoning. Now, let's begin our journey into the heart of cosmic origins, where we all discover how the universe might have solved the ultimate paradox by creating everything from nothing while perfectly conserving energy in the process. Chapter 1. Conservation Mystery. The conservation of energy stands as one of the most fundamental and inviolable principles in all of physics, stating that the total amount of energy in any isolated system remains constant over time. Energy can change forms. Kinetic energy can become heat, chemical energy can become light. Mass can become energy according to Einstein's E equals mc, but the total amount never increases or decreases. This principle governs everything from simple mechanical systems to the most complex processes in stars and galaxies, making the Big Bang's apparent creation of cosmic energy one of the most disturbing paradoxes in science. The mathematical statement of energy conservation appears deceptively simple. ddt equals 0, meaning the rate of change of total energy with respect to time equals 0. But this simplicity conceals profound implications for how we understand causality, physical law, and the nature of existence itself. If energy truly cannot be created or destroyed, then every joule of energy currently in the universe must have existed in some form since the beginning of time, or else our most basic understanding of physics is fundamentally flawed. Dr. Emmy Noether proved in 1915 that energy conservation emerges directly from the mathematical symmetry of physical laws under time translation. Noether's theorem demonstrates that every continuous symmetry in physics corresponds to a conservation law, with energy conservation arising from the fact that the laws of physics don't change over time. This deep connection between symmetry and conservation makes energy conservation not just an empirical observation, but a mathematical consequence of the fundamental structure of physical law. The historical development of energy conservation reveals how this principle emerged from careful study of mechanical systems, thermodynamics, and electromagnetic phenomena. James Joule's precise experiments in the mid-1800s demonstrated the mechanical equivalent of heat, showing that mechanical work and thermal energy are interconvertible according to exact mathematical relationships. Later discoveries revealed that chemical energy, nuclear energy, and even mass itself are forms of energy subject to conservation principles. But applying energy conservation to cosmology creates immediate conceptual difficulties. In a finite closed system, we can clearly define the total energy and track how it transforms over time. But the universe appears to be infinite in spatial extent, making it unclear how to define total energy in any meaningful way. Moreover, the expansion of space itself complicates energy conservation in ways that don't arise in terrestrial physics. The energy density of electromagnetic radiation decreases as the universe expands because photons become redshifted to longer wavelengths and lower energies. This cosmological redshift appears to violate energy conservation. Energy seems to disappear as light travels through expanding space. Where does this lost energy go? And how can we reconcile this apparent violation with the fundamental principle that energy must be conserved? Einstein's general relativity provides a framework for understanding energy conservation in curved spacetime, but it reveals that energy conservation becomes much more subtle when gravity and spacetime curvature are involved. In general relativity, there is no unique way to define the total energy of a gravitational system, and the concept of global energy conservation becomes ambiguous in universes that are not asymptotically flat. The problem becomes even more acute when we consider the Big Bang itself. Standard cosmological models suggest that the universe began in an extremely hot, dense state that contained enormous amounts of energy packed into a region smaller than a subatomic particle. As the universe expanded and cooled, this energy transformed into the matter and radiation we observe today. But the total amount of energy appears to have been created from nothing during the first moments of cosmic expansion. Quantum mechanics adds another layer of complexity to the conservation mystery through the uncertainty principle, which allows energy conservation to be violated for extremely brief periods of time. The energy-time uncertainty relation, delta E, delta T, is greater than or equal to A2, permits spontaneous creation of particle-antiparticle pairs from vacuum fluctuations, provided they annihilate quickly enough that the violation falls within the uncertainty limits. These quantum fluctuations are not merely theoretical possibilities, but have been confirmed through careful experiments that detect the Casimir effect, measurable forces arising from quantum vacuum energy. The existence of vacuum energy suggests that empty space actually contains enormous amounts of fluctuating energy that could potentially serve as a reservoir for cosmic creation processes. The cosmological constant problem reveals another aspect of the energy conservation mystery. Quantum field theory predicts that vacuum energy should contribute to the cosmological constant with a value roughly 10^120 times larger than observations allow. This spectacular disagreement between theory and observation suggests that our understanding of vacuum energy and its role in cosmic evolution remains fundamentally incomplete. Dark energy, which appears to comprise roughly 70% of the universe's total energy budget, presents additional challenges for understanding cosmic energy conservation. This mysterious component seems to have a constant energy density throughout space, meaning that the total amount of dark energy increases as the universe expands. Where does this additional dark energy come from, and how can its apparent creation be reconciled with energy conservation principles? The anthropic principle offers one perspective on the energy conservation mystery by suggesting that we observe a universe with particular energy properties, because only such a universe could give rise to observers like ourselves. Perhaps energy conservation is violated during Big Bang events, but only universes with specific energy budgets develop the complexity necessary for life and intelligence. Attempts to resolve the conservation mystery have led to increasingly exotic theoretical proposals. Some physicists suggest that the universe might be a closed time-like curve where energy flows in a loop, eliminating the need for external creation. Others propose that the Big Bang represents a phase transition in a higher dimensional space where energy conservation operates on scales beyond our observable universe. The many worlds interpretation of quantum mechanics provides another potential resolution by suggesting that all possible energy configurations exist simultaneously across parallel universes. From this perspective, our universe appears to violate energy conservation only because we observe one particular branch of a vast quantum superposition where conservation is maintained across all branches collectively. String theory and other approaches to quantum gravity suggest that energy conservation might be modified at the Planck scale where spacetime itself becomes quantized. In these theories, the classical notion of energy conservation might be replaced by more fundamental conservation laws governing the dynamics of strings, brains, or other exotic objects that comprise spacetime at its most basic level. Experimental tests of energy conservation in cosmological contexts remain extremely challenging because we cannot perform controlled experiments on the universe as a whole. However, precision measurements of cosmic microwave background radiation, supernova observations, and gravitational wave astronomy are beginning to provide tests of whether energy conservation operates as expected on cosmic scales. The psychological impact of the conservation mystery extends beyond technical physics to challenge our basic intuitions about causality and existence. If the universe can create energy from nothing, it suggests that the cosmos operates according to principles that transcend our everyday understanding of cause and effect, opening possibilities for phenomena that seem to violate logical reasoning. Philosophical implications of the mystery include questions about whether physical laws are truly universal or might be emergent properties that arise from more fundamental principles. If energy conservation can be violated during cosmic creation events, it suggests that the laws of physics themselves might have origins and might not be eternal, unchanging features of reality. Dr. Lawrence Krauss from Arizona State University reflects on the profound nature of this mystery. The question of where cosmic energy came from forces us to confront the deepest issues in physics and philosophy. It challenges our understanding of causality, natural law, and the very concept of existence itself. The answer may require us to fundamentally reimagine what we mean by something and nothing. The conservation mystery demonstrates how cosmic questions can illuminate fundamental physics principles while revealing the limitations of our current theoretical frameworks. Understanding how the universe apparently violates energy conservation may be the key to developing new physics that can describe the origin of spacetime itself. Modern approaches to the conservation mystery increasingly recognize that the question itself might be based on incorrect assumptions about the nature of energy, time, and causality. Perhaps the apparent paradox arises from trying to apply concepts developed for understanding terrestrial physics to cosmic phenomena that operate according to entirely different principles. The conservation mystery continues to drive cutting-edge research in theoretical physics, inspiring new mathematical frameworks and experimental techniques, while forcing physicists to question their most basic assumptions about how the universe works at its deepest level. Chapter 2. Energy Accounting. Calculating the total energy content of the observable universe represents one of the most ambitious accounting projects ever attempted, requiring astronomers and physicists to inventory everything from the kinetic energy of galaxies speeding away from us to the binding energy in atomic nuclei, from the gravitational potential energy stored in cosmic structures to the mysterious dark energy that drives cosmic acceleration. This cosmic energy census reveals numbers so large they challenge human comprehension while providing crucial insights into how the Big Bang could have created such enormous amounts of energy without violating conservation laws. The observable universe contains approximately 1,080 atoms, each representing rest mass energy according to Einstein's mass energy equivalence, EMC. A typical hydrogen atom has a mass of about 1.67 times 10⁻27 kilograms, corresponding to an energy of roughly 938 MeV when converted completely to energy. Multiplying by the total number of atoms yields a staggering figure. The rest mass energy of all ordinary matter in the observable universe equals approximately 1,069 joules. To put this number in perspective, this amount of energy exceeds the total energy output of our Sun over its entire 10 billion year lifetime by a factor of more than 1,050. If we could somehow convert all the matter in the observable universe directly into energy, the resulting explosion would be visible from distances measured in billions of light years, far outshining any supernova or gamma ray burst ever observed. Dr. Sean Carroll from Caltech, who has extensively studied cosmic energy budgets, explains the challenge. When we try to account for all the energy in the universe, we quickly realize we're dealing with numbers so large they become almost meaningless. The real question isn't just how much energy exists, but how such enormous amounts could have appeared without violating the most fundamental principles of physics. But ordinary matter represents only about 5% of the universe's total energy content. Dark matter, which interacts gravitationally but not electromagnetically, comprises roughly 27% of the cosmic energy budget. The total energy in dark matter exceeds the energy in ordinary matter by more than a factor of 5, corresponding to approximately 5 YY joules throughout the observable universe. Dark energy presents an even more mysterious component, accounting for roughly 68% of the universe's total energy density. Unlike matter and radiation, dark energy appears to have a constant energy density throughout space, meaning the total amount of dark energy increases as the universe expands. Current estimates suggest that dark energy contributes approximately 1.3 times Y joules to the cosmic energy budget. The energy contained in electromagnetic radiation, starlight, cosmic microwave background radiation, radio waves from galaxies, and all other forms of light represents a much smaller fraction of the total, roughly 0.005% of the cosmic energy density. However, the absolute amount still reaches approximately 5,1066 joules, equivalent to the mass energy of roughly a billion Earth-mass planets. Kinetic energy from cosmic expansion adds another significant component to the energy inventory. Every galaxy is moving away from us at velocities that increase with distance, according to Hubble's law. The kinetic energy of galactic recession velocities contributes roughly 1,068 joules to the cosmic energy budget, though calculating this precisely requires careful consideration of reference frames in expanding spacetime. Gravitational binding energy represents one of the most complex components to calculate because gravity in general relativity doesn't have a well-defined energy density. However, the binding energy that holds galaxy clusters together keeps galaxies bound despite cosmic expansion, and maintains the structure of stars and planets represents enormous negative contributions to the cosmic energy budget that partly offset the positive energy in matter and radiation. The cosmic microwave background radiation, which fills all of space with thermal radiation at 2.7 Kelvin, contains approximately 41058 joules of energy throughout the observable universe. This radiation represents the cooled remnant of the intense heat that filled the early universe, providing direct observational evidence for the Big Bang's enormous energy release. Neutrinos, which were created in vast numbers during the Big Bang and continue to permeate space at a density of roughly 300 particles per cubic centimeter, contribute approximately 1,066 joules to the cosmic energy budget. These nearly massless particles travel at close to light speed and interact so weakly with matter that they pass through entire planets without being absorbed. The energy stored in cosmic magnetic fields, though difficult to measure precisely, adds another component to the energy inventory. Galaxy clusters and individual galaxies possess magnetic fields that store energy at levels comparable to the kinetic energy of turbulent gas motions, contributing perhaps 1,065 joules to the total cosmic energy budget. Rotational energy from spinning galaxies, neutron stars, and black holes represents another kinetic energy component that must be included in comprehensive energy accounting. The Milky Way's rotation, for example, represents roughly 1,058 joules of kinetic energy, and similar contributions from billions of other galaxies throughout the observable universe add up to significant amounts. The energy scales involved in cosmic accounting often exceed those familiar from terrestrial physics by factors that challenge mathematical notation. For comparison, the total energy consumed by human civilization throughout history equals roughly 1,021 joules, less than 1 part in 1,048 of the universe's total energy content. Vacuum energy presents perhaps the most puzzling component of cosmic energy accounting. Quantum field theory suggests that even empty space contains zero-point energy fluctuations that should contribute enormously to the cosmic energy density. However, the predicted vacuum energy density exceeds observations by factors of 10,120, creating the cosmological constant problem that remains unsolved. The energy density of space itself, as measured by the cosmological constant, equals approximately 6·10⁻27 kilograms per cubic meter when expressed in mass units. This tiny density becomes enormous when multiplied by the volume of the observable universe, yielding the dark energy component that dominates cosmic energy accounting. Precision measurements of cosmic energy densities have been achieved through multiple observational techniques, including supernova observations that revealed cosmic acceleration, cosmic microwave background measurements that determine curvature and composition, and galaxy surveys that map large-scale structure formation. The Planck satellite's measurements of cosmic microwave background anisotropies have provided the most precise determinations of cosmic energy densities, revealing that the universe contains 68.3% dark energy, 26.8% dark matter, and 4.9% ordinary matter with tiny contributions from radiation and neutrinos. These measurements reveal a remarkable fact. The total energy density of the universe appears to be extremely close to the critical density needed for flat spacetime geometry. This critical density equals approximately 9.5 times 10⁻27 kilograms per cubic meter, and observations suggest the universe's actual density differs from this critical value by less than 1%. The flatness of cosmic geometry has profound implications for cosmic energy accounting because it suggests that the universe's total energy might be exactly zero when gravitational potential energy is properly included. In a flat universe, the positive energy in matter and radiation exactly balances the negative gravitational potential energy, creating a cosmic free lunch where enormous amounts of energy can be created without violating conservation laws. Modern energy accounting also must consider the energy contained in cosmic defects like cosmic strings, domain walls, and monopoles that might have formed during phase transitions in the early universe. While these exotic objects haven't been definitively observed, they could potentially contribute significant amounts to the cosmic energy budget. The temporal evolution of cosmic energy densities adds complexity to energy accounting because different components scale differently as the universe expands. Matter density decreases as the inverse cube of the scale factor. Radiation density decreases as the inverse fourth power, but dark energy density remains approximately constant. Future observations using next-generation telescopes and gravitational wave detectors promise to refine cosmic energy accounting by measuring previously undetectable components and improving precision on known contributions. These measurements will provide crucial tests of whether the universe's energy budget is truly balanced and whether our accounting procedures are correct. Dr. Rocky Kolb from the University of Chicago reflects on cosmic energy accounting. When we add up all the energy in the universe, we get numbers so large they're almost meaningless to human intuition. But the real surprise is that when we include gravitational energy properly, the books might actually balance perfectly at zero. The enterprise of cosmic energy accounting reveals both the magnificent scale of the universe and the elegant possibilities for its creation from nothing, demonstrating how precise measurements and careful theoretical analysis can illuminate the deepest questions about cosmic origins and energy conservation. Understanding cosmic energy accounting provides the foundation for exploring how such enormous energy contents could arise during the Big Bang while respecting conservation laws, setting the stage for investigating the quantum mechanical processes that might create universes from vacuum fluctuations. Chapter 3. Quantum Vacuum. The quantum vacuum represents one of the most counterintuitive concepts in modern physics, a state that appears empty but actually seethes with energy fluctuations that spontaneously create and destroy particle pairs, generate measurable forces, and potentially provide the energy reservoir from which entire universes can emerge. Understanding the quantum vacuum is crucial for resolving the Big Bang energy paradox because it reveals how nothing is actually something in quantum mechanics, and how enormous amounts of energy can be borrowed from vacuum fluctuations without violating conservation laws. In classical physics, a vacuum represents the complete absence of matter and energy, a state of true nothingness where no particles exist and no fields carry energy. But quantum mechanics reveals that such a classical vacuum is impossible due to the uncertainty principle, which prevents all properties of a quantum system from being simultaneously well-defined. Even in the apparent emptiness of space, quantum fields undergo constant fluctuations that create temporary particle-antiparticle pairs. These vacuum fluctuations are not mere mathematical abstractions, but have observable consequences that have been confirmed through precise experiments. The Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948, demonstrates that vacuum fluctuations can generate measurable forces between conducting plates, placed extremely close together in seemingly empty space. Dr. Steven Weinberg from the University of Texas, who won the Nobel Prize for his work on unified field theory, explains the profound nature of the quantum vacuum. The vacuum isn't empty. It is the most complex state we know in physics, filled with quantum fields oscillating at every possible frequency. Understanding the vacuum may be the key to understanding how the universe itself came into existence. The energy density of vacuum fluctuations can be calculated using quantum field theory, though the calculation yields a disturbing result known as the cosmological constant problem. When physicists add up the zero-point energies of all quantum fields, they get an energy density roughly 10,120 times larger than what observations of cosmic expansion allow. This represents the largest discrepancy between theory and observation in all of physics. The mathematical description of vacuum energy emerges from the fact that quantum fields can never reach exactly zero energy, even in their lowest energy state. Each mode of oscillation contributes a zero-point energy of omega 2, whereas Planck's constant and omega is the oscillation frequency. Since there are infinitely many possible oscillation modes with arbitrarily high frequencies, the total vacuum energy appears infinite. Renormalization techniques in quantum field theory attempt to handle these infinities by subtracting them away. But this mathematical procedure doesn't resolve the physical question of how much energy the vacuum actually contains. The subtracted infinities must go somewhere, and understanding their fate becomes crucial for cosmic energy accounting. The quantum vacuum plays a central role in modern theories of cosmic inflation, which propose that the universe underwent a period of exponential expansion driven by the energy density of a quantum field trapped in a false vacuum state. During inflation, this false vacuum energy creates a repulsive gravitational effect that drives exponential expansion while remaining nearly constant in density. Vacuum decay processes provide potential mechanisms for universe creation through quantum tunneling events. In this picture, our universe might have nucleated as a bubble of true vacuum expanding within a metastable false vacuum, with the energy difference between vacuum states providing the energy content of the expanding bubble universe. The eternal inflation scenario takes vacuum-driven universe creation to its logical extreme, proposing that false vacuum states continuously decay into bubble universes through quantum fluctuations, creating an infinite multiverse where each Big Bang represents a local vacuum decay event rather than a unique cosmic origin. Vacuum entanglement creates quantum correlations between widely separated regions of space that could potentially explain how the Big Bang created a universe with nearly uniform properties despite having no time for causal communication. The quantum vacuum's entanglement structure might provide the initial correlations needed to explain cosmic microwave background uniformity. The Unruh effect demonstrates that the nature of the vacuum depends on the observer's acceleration, with accelerated observers detecting thermal radiation in states that appear vacuum-like to inertial observers. This observer dependence suggests that vacuum energy might not have an absolute meaning, but could depend on cosmological reference frames. Virtual particles in vacuum fluctuations can become real particles when sufficient energy is supplied to separate them before they annihilate. High-energy processes near black holes during cosmic inflation or in particle accelerators can promote virtual particles to real existence, potentially providing mechanisms for matter creation from vacuum energy. The quantum vacuum's energy momentum tensor violates all the standard energy conditions that classical matter satisfies, allowing it to have negative pressure that could drive cosmic acceleration. This exotic equation of state makes vacuum energy a natural candidate for dark energy, though the predicted magnitude remains problematically large. Vacuum polarization effects modify the electromagnetic properties of space by creating virtual particle-antiparticle pairs that respond to external fields. These effects have been measured precisely in atomic physics experiments and confirm that the vacuum actively participates in electromagnetic interactions rather than merely providing a passive background. The vacuum structure becomes even more complex in curved spacetime, where the definition of vacuum becomes observer-dependent and field modes can mix in ways that do not occur in flat spacetime. The Hawking effect demonstrates that vacuum fluctuations near black hole horizons can create thermal radiation, showing how curved spacetime geometry affects vacuum energy. Spontaneous symmetry breaking in the quantum vacuum plays a crucial role in particle physics, where the vacuum state doesn't exhibit the full symmetry of the underlying physical laws. The Higgs mechanism relies on vacuum structure to generate particle masses while hiding the underlying symmetries that govern fundamental interactions. Vacuum engineering represents a speculative but theoretically interesting possibility where advanced civilizations might manipulate vacuum energy for technological purposes. while extracting net energy from vacuum fluctuations appears impossible due to conservation laws. Localized modifications of vacuum structure might enable exotic phenomena like negative energy densities. The quantum vacuum's role in cosmology extends beyond energy provision to include structure formation through vacuum, fluctuations that get amplified during inflation to create the density perturbations that eventually grow into galaxies and larger cosmic structures. The cosmic microwave background's temperature variations provide observational evidence for this vacuum-driven structure formation. Laboratory studies of vacuum energy continue to reveal new aspects of quantum field behavior, including recent measurements of dynamical Casimir effects, where accelerated boundaries can create real photons from vacuum fluctuations. These experiments provide direct confirmation that vacuum energy can be converted into observable particles under appropriate conditions. The information content of the quantum vacuum presents additional puzzles for understanding cosmic origins. If the vacuum contains infinite amounts of both energy and information, how do finite universes with specific properties emerge from this infinite reservoir? Understanding vacuum information might be as important as understanding vacuum energy for cosmic creation theories. Analog vacuum systems in condensed matter physics provide laboratory models for studying vacuum fluctuations and their effects. Superconductors, superfluids, and other exotic materials exhibit vacuum-like states with controllable properties that can test theoretical predictions about vacuum behavior in cosmological contexts. Future theoretical developments in quantum gravity might resolve the vacuum energy problem by revealing how gravity affects vacuum fluctuations on the smallest scales. String theory, loop quantum gravity, and other approaches suggest that spacetime itself might be quantized in ways that regulate vacuum energy at the Planck scale. Dr. Frank Wilczek from MIT reflects on the vacuum's cosmic significance. The quantum vacuum is nature's most subtle and powerful creation, a state that appears empty but contains infinite potential for creating matter, energy, and entire universes. Understanding how the vacuum works may be the key to understanding how everything came from nothing. The quantum vacuum reveals that the concept of nothingness has no meaning in quantum mechanics, where even the absence of particles and fields corresponds to a rich quantum state with complex structure and unlimited creative potential for generating cosmic phenomena. Understanding the quantum vacuum provides crucial insights into how the Big Bang might have borrowed enormous amounts of energy from vacuum fluctuations while respecting conservation laws, setting the stage for exploring how inflation theory amplifies vacuum effects to cosmic scales. Chapter 4. Inflation theory. Cosmic inflation represents one of the most revolutionary and successful theories in modern cosmology, proposing that the universe underwent a brief period of exponential expansion during its first fraction of a second, driven by the energy density of a quantum field trapped in a false vacuum state. This theory not only explains many puzzling features of our observable universe, but also provides an elegant solution to the Big Bang energy paradox by showing how quantum fields can create enormous amounts of matter and energy while maintaining perfect energy conservation. The inflation theory emerged from attempts to solve several fundamental problems with the standard Big Bang model, including the horizon problem, the flatness problem, and the monopole problem. These issues suggested that the early universe possessed special initial conditions that seemed incredibly fine-tuned, but inflation demonstrates how exponential expansion can dynamically create these conditions regardless of initial setup. Dr. Alan Guth from MIT proposed the original inflation theory in 1980, inspired by the realization that certain phase transitions in the early universe could create regions of false vacuum with enormous energy densities that would drive exponential expansion. Guth's insight was recognizing that such expansion could solve multiple cosmological puzzles simultaneously while providing a natural mechanism for universe creation. The mathematical framework of inflation relies on scalar fields, quantum fields that have the same value everywhere in space at any given time. When a scalar field becomes trapped in a false vacuum state, it acts like a cosmological constant with positive energy density and negative pressure. Einstein's field equations show that negative pressure creates repulsive gravity that drives exponential expansion. During inflation, the universe's scale factor grows exponentially according to AT equals a 0 EX/PHT, where h is the Hubble parameter determined by the inflated field's energy density. This exponential expansion can increase the universe's size by factors of 1030 or more in time periods shorter than 10 to 32 seconds, creating cosmic regions much larger than light could have traveled. The horizon problem illustrates why inflation is needed to explain cosmic microwave background uniformity. In standard Big Bang cosmology, regions of the cosmic microwave background separated by more than about 1 degree on the sky were never in causal contact, yet they have nearly identical temperatures. Inflation solves this by expanding a small causally connected region to cosmic scales. The flatness problem arises because the universe's geometry appears to be extremely close to perfect flatness, requiring the total energy density to equal the critical density with precision exceeding 1 part in 1060. Inflation explains this remarkable fine-tuning by showing that exponential expansion drives any initial curvature towards zero, making flatness a natural outcome rather than a special initial condition. Quantum fluctuations during inflation provide the seeds for all cosmic structure, from galaxies to galaxy clusters to the largest observable structures in the universe. The inflated field undergoes quantum fluctuations that get frozen into classical density perturbations when their wavelengths exceed the Hubble radius during exponential expansion. These density perturbations follow a nearly scale-invariant power spectrum predicted by inflation theory and confirmed by precision measurements of cosmic microwave background anisotropies. The excellent agreement between theoretical predictions and observational data provides strong evidence that inflation actually occurred during the universe's first moments. The energy source for inflation comes from the potential energy of the inflated field trapped in a false vacuum state. As the field slowly rolls toward its true vacuum configuration, it releases enormous amounts of energy that get converted into the matter and radiation that fill the post-inflationary universe through a process called reheating. Reheating occurs when the inflated field finally reaches its true vacuum and begins oscillating around the minimum of its potential. These oscillations couple to other quantum fields, creating particles and antiparticles that thermalize to form the hot, dense plasma that characterizes the standard Big Bang phase of cosmic evolution. The total energy available for reheating depends on the difference between false and true vacuum energy densities, which can be enormous without violating energy conservation. The false vacuum energy gets converted into kinetic and rest mass energy of particles, while gravitational potential energy accounts for the negative energy needed to balance the cosmic energy budget. Eternal inflation extends the basic inflation picture by recognizing that quantum fluctuations can cause some regions to inflate even more than others, creating a fractal-like structure where inflation never completely ends but continues forever in some locations while ending in others to create bubble universes. The multiverse naturally emerges from eternal inflation because different bubble universes can have different physical properties depending on how the inflated field symmetries break during reheating. This provides a framework for understanding why our universe has the particular physical constants and laws that we observe. Chaotic inflation, developed by Andre Linde, shows that inflation can occur from generic initial conditions rather than requiring special symmetric states. In this scenario, inflation begins whenever quantum field values exceed the Planck scale in any region, making universe creation a natural consequence of quantum fluctuations in any high-dimensional space. The string theory landscape provides a concrete realization of eternal inflation, where the inflated field corresponds to the positions of branes in high-dimensional space. Different brain configurations correspond to different vacuum states with different cosmological constants and particle physics, creating a vast landscape of possible universes. Observational tests of inflation have been remarkably successful, with precision measurements confirming multiple predictions, including the spectrum of density perturbations, the relationship between scalar and tensor fluctuations, and the statistical properties of cosmic microwave background anisotropies. Gravitational waves from inflation represent a smoking gun signature that could definitively confirm the theory. Quantum fluctuations of spacetime itself during inflation should create a background of primordial gravitational waves, with characteristic polarization patterns in the cosmic microwave background. The detection of B-mode polarization in the cosmic microwave background would provide direct evidence for inflationary gravitational waves while measuring the energy scale of inflation. Current experiments are approaching the sensitivity needed to detect these signals or place meaningful constraints on inflation models. Energy conservation during inflation operates through the interplay between positive energy in the inflatoned field and negative gravitational potential energy. As the universe expands exponentially, the total positive energy increases enormously. But this is exactly balanced by increasingly negative gravitational binding energy. The gauge theory dual of inflation provides alternative descriptions where the exponential expansion corresponds to strongly coupled quantum field theory evolution. These dualities suggest that inflation might be described equivalently using quantum mechanical systems without gravity, providing new perspectives on how energy conservation operates during universe creation. Non-Gaussianity in cosmic microwave background fluctuations provides additional tests of specific inflation models by measuring how quantum fluctuations deviate from perfect random noise. Different inflaton potentials predict different non-Gaussian signatures that can distinguish between competing theories. The Trans-Planckian problem in inflation asks whether quantum fluctuations that originated at sub-Planckian scales can reliably be extrapolated to cosmic scales. Resolving this problem requires understanding quantum gravity effects that might modify standard inflation predictions. Future cosmological observations using next-generation telescopes and gravitational wave detectors promise to test inflation theory with unprecedented precision while potentially revealing whether our universe is embedded in a larger multiverse structure created by eternal inflation. Modified gravity theories provide alternative explanations for cosmic acceleration and structure formation that might mimic inflation signatures while operating through different physical mechanisms. Distinguishing between inflation and modified gravity requires precise measurements of multiple observational signatures. Dr. Andrew Lind from Stanford University reflects on inflation's significance. Inflation shows us that the universe can create enormous amounts of matter and energy from quantum vacuum fluctuations while perfectly conserving energy through gravitational effects. This reveals the universe as the ultimate free lunch. Everything from nothing, with perfect bookkeeping. Inflation theory demonstrates that the Big Bang energy paradox dissolves when we properly account for gravitational potential energy and understand how quantum fields can amplify vacuum fluctuations to cosmic scales, providing a complete mechanism for universe creation that respects all conservation laws. Understanding inflation reveals how quantum mechanics and general relativity work together to create universes from vacuum fluctuations while maintaining energy conservation through the delicate balance between positive matter energy and negative gravitational potential energy. Chapter 5. Gravitational energy. Gravitational energy represents one of the most subtle and profound concepts in physics, fundamentally different from other forms of energy because gravity in Einstein's general relativity is not a force, but a manifestation of spacetime curvature itself. Understanding gravitational energy is crucial for resolving the Big Bang energy paradox, because it reveals how enormous amounts of positive energy in matter and radiation can be perfectly balanced by equally enormous amounts of negative gravitational potential energy, creating the possibility for cosmic free lunches where entire universes emerge from energy budgets that sum to exactly zero. In Newtonian physics, gravitational potential energy is always negative, representing the energy required to completely separate gravitationally bound objects to infinite distance. Two masses attracted by gravity possess negative potential energy proportional to g(m)(j)(m)r, where g is the gravitational constant and r is the separation distance. This negative energy becomes more negative as objects move closer together, releasing energy that can be converted to kinetic energy or heat. But general relativity reveals that the concept of gravitational energy becomes much more complex and subtle when spacetime curvature is properly included. In Einstein's theory, gravity is not a force that acts between objects, but rather the manifestation of how mass and energy curve the geometry of spacetime itself. This geometric interpretation makes it difficult to define gravitational energy in a unique, observer-independent way. Dr. Kip Thorne from Caltech, who won the Nobel Prize for Gravitational Wave Research, explains the complexity. Gravitational energy in general relativity is like the smile of the Cheshire Cat. You know it's there because of its effects, but trying to pin down exactly where it is and how much exists leads to fundamental ambiguities that reveal deep truths about the nature of spacetime. The Einstein field equations relate spacetime curvature to matter and energy content, but they don't provide a unique prescription for dividing the total energy of a gravitational system into matter energy and gravitational energy components. Different mathematical approaches yield different answers, suggesting that the distinction between these energy types might be more conceptual than fundamental. However, in certain special cases, gravitational energy can be calculated unambiguously. For asymptotically flat spacetimes, regions that become flat far from all matter, the ADM energy provides a well-defined total energy that includes both matter and gravitational contributions. This total energy can be positive, negative, or zero depending on the specific mass and geometry configuration. The negative energy theorem in general relativity states that the gravitational binding energy of any bounded system is always negative and exactly equals the negative of the total kinetic and rest mass energy when the system is in gravitational equilibrium. This profound result means that gravitationally bound systems always have negative total energy from the perspective of distant observers. For the universe as a whole, the situation becomes even more interesting. If spacetime is perfectly flat, as observations suggest with high precision, then the total energy of the universe, including both positive matter energy and negative gravitational potential energy, equals exactly zero. This remarkable result means the universe represents the ultimate free lunch, infinite amounts of matter and energy created from nothing. The calculation of cosmic gravitational energy requires careful consideration of boundary conditions and reference frames. In a closed universe, the total energy is well defined and equals zero due to the geometry of closed spacetime. In an open or flat universe, the energy calculation depends on how we define the reference state at spatial infinity. The Friedmann equations that govern cosmic expansion can be rewritten to show explicitly how gravitational potential energy balances matter and radiation energy. In a flat universe, the kinetic energy of expansion exactly equals the gravitational binding energy, making the total energy zero at all times during cosmic evolution. This energy balance explains how the universe can create enormous amounts of matter and radiation during inflation without violating energy conservation. As the universe expands exponentially, the total positive energy in matter and fields increases dramatically, but this is exactly matched by increasingly negative gravitational potential energy that maintains the zero energy balance. The concept of gravitational potential energy becomes especially important during cosmic inflation, when the false vacuum energy density drives exponential expansion. The enormous positive energy in the inflaton field gets balanced by equally enormous negative gravitational potential energy, allowing the universe to create vast amounts of energy while maintaining perfect conservation. Gravitational waves carry away energy from accelerating masses, providing direct observational evidence for gravitational energy. When binary black holes spiral toward merger, they lose orbital energy by radiating gravitational waves, confirming that gravitational binding energy can be converted into propagating waves that carry energy to infinity. The detection of gravitational waves by LIGO and other observatories has enabled direct measurements of how much energy gets radiated during black hole mergers. These measurements confirm general relativity's predictions about gravitational energy while providing tests of energy conservation in extremely strong gravitational fields. Dark energy complicates the cosmic energy accounting because it appears to have positive energy density that remains constant as the universe expands. This means the total amount of dark energy increases over time, potentially violating energy conservation unless it's balanced by corresponding changes in gravitational potential energy. The holographic principle suggests that gravitational energy might be encoded on boundary surfaces rather than distributed throughout space. In this framework, the bulk gravitational energy of any region equals the information content of its boundary, providing new perspectives on how gravitational energy relates to quantum information. ADS, CFT, correspondence demonstrates that gravitational physics in curved spacetime can be equivalent to non-gravitational quantum field theory on the boundary. In this duality, gravitational energy in the bulk corresponds to excitation energies in the boundary theory, providing concrete examples of how gravitational energy relates to other forms of energy. The energy-momentum tensor of gravitational fields themselves cannot be defined uniquely in general relativity, leading to the famous energy-momentum problem of gravitation. Various pseudotensors have been proposed to represent gravitational energy density, but none are generally covariant, reflecting the deep geometric nature of gravitational phenomena. Quantum gravity theories attempt to resolve the gravitational energy problem by treating spacetime itself as a quantum mechanical system. In these theories, gravitational energy might emerge from quantum entanglement between different regions of space, providing new perspectives on how energy conservation operates when spacetime itself is quantized. The positive energy theorem, proved by Richard Schoen and Xingtong You, states that any asymptotically flat spacetime satisfying reasonable physical conditions must have non-negative total energy, with zero energy only for flat Minkowski spacetime. This theorem constrains possible cosmic geometries while confirming that our universe could indeed have zero total energy. Gravitational energy storage in cosmic structures provides another perspective on cosmic energy accounting. Galaxy clusters represent enormous gravitational potential wells that store vast amounts of negative energy, while the kinetic energy of galaxies falling into these wells represents positive energy that balances the gravitational binding. The formation of structure in the universe can be understood as a process where initially smooth matter distributions develop, gravitational potential wells that convert kinetic energy into binding energy. This structure formation process conserves total energy while redistributing it between kinetic, potential, and thermal components. Gravitational lensing effects provide observational windows into gravitational energy by revealing how massive objects curve spacetime and affect light propagation. Strong lensing events demonstrate that gravitational potential wells can store enormous amounts of negative energy while creating observable effects on electromagnetic radiation. Future gravitational wave observations with space-based detectors like LISA will provide unprecedented sensitivity to gravitational energy changes throughout cosmic history. These observations might detect energy loss from primordial black hole populations or reveal new sources of gravitational radiation from exotic cosmic phenomena. The thermodynamics of gravitational systems reveals unusual properties where systems can have negative heat capacity, meaning they get hotter when they lose energy. This counterintuitive behavior reflects the long-range nature of gravitational interactions and has important implications for understanding cosmic energy evolution. Dr. Sean Carroll from Caltech reflects on gravitational energy's cosmic significance. Gravitational energy is the universe's ultimate accounting system. It allows enormous amounts of positive energy to be created from nothing by balancing them with equally enormous amounts of negative potential energy. This cosmic bookkeeping makes the Big Bang possible without violating energy conservation. Understanding gravitational energy reveals how the universe can create vast amounts of matter and radiation while maintaining perfect energy conservation through the balance between positive matter energy and negative gravitational potential energy, solving the apparent paradox of Big Bang energy creation. Gravitational energy demonstrates that the universe operates according to accounting principles far more sophisticated than our everyday experience suggests, where the creation of everything from nothing becomes possible through the elegant mathematics of curved spacetime, geometry, and energy momentum conservation.